Good morning, everybody, and welcome to another episode of High Performance Delta. Today, I'm joined by Bartosz, who doesn't really need any sort of introduction. If you've been in the Spark community for the past over 10 years now, you've probably been checking out Waiting for Code to learn how to, do anything in Spark. I'm very excited today to talk more about data design patterns, then also how those apply to streaming data design patterns as well. And so without really further ado, I'm going to kick this over to Bartosz, and let's just get going.
New design patterns. And that's kind of good question to ask, because design patterns in general are kind of high-level concepts that you don't necessarily connect or link to any specific technology, but turns out that if you want to implement them on production, you need real tools behind. And Delta Lake is one of the tools that is present in the book. And that kind of inspired this webinar, where together with Scott, we are going to cover a few data engineering design patterns in Delta Lake. So we are going to discover Delta Lake features from data engineering design patterns. So maybe you can click, Scott. Yeah, thank you. And the next one. And this is a kind of high-level architecture we are going to discuss in this session. It's common. Yeah, so we have some kind of data sources and technologies that we are going to use to implement real jobs and real tables. For the tables, it will be Delta Lake, and for the technologies for the jobs, it will be Apache Spark. And all starts with the change data capture that streamlines the changes from the source table and addresses at the same time pretty greatly the incremental loader issues with hard delays. Later, once we process the data, we have three patterns: the fast metadata cleaner to ensure the idempotency very cheaply with metadata operations, metadata decorator that is here to add some kind of additional context to the data we are writing, to the commits we are doing on Delta Lake, and finally the constraints enforcer that gives an extra security and protection against data quality issues at the source level, so without any extra job running to control them. And from that, we have two different roads. The first is towards another Delta Lake table, where we are going to use the pass-through replicator. And the other one on the bottom line uses a custom Apache Spark job that implements the parallel split design pattern, where using a common set of transformations, we are going to write the same data set, or the same data set with the similar transformations into different places. So technically it will be different because you can do some other transformations on top of these common transformations, but the idea is that you process the same data set in the same job and write in two different tables. Yeah, you can click now, Scott. Yeah, that's the features we are going to discover today on my end. The change data feed for the change data capture, Truncate table for the fast metadata cleaner. We could use here also the drop table, but Truncate table, it's kind of more handy, I think, especially when you want to manage schemas in a different place, like for example, your Terraform provider or libcubase like tools, where you can version the schemas as well. For the metadata decorator, we are going to use a user metadata feature. For the constraints enforcer, the constraints on the Delta Lake tables, and finally clone for pass-through replicator, and idempotent writer for the parallel split. Yeah, we can now move on to the first of the Delta Lake features, which is the change data feed. So the change data feed is great when you want to streamline the changes made on top of your table. And as you can see on the screen, we have some kind of streaming reader consuming these change data feed records. And you can see that there is no issue with hard delays. So the hard delays are pretty difficult to manage, or even impossible to manage in incremental loading patterns, because the records are simply disappearing when you delete something from the table. And with change data feed, you can streamline and record any changes made on your table, even the hard delays, or you can even do some quite fancy stuff when you compare the data in update or merge operations with the version before and after the changes. And you can enable this feature per table. So with Delta, enable change data feed property, or generally in Spark session with the corresponding default. And in the next slide, we are going to see kind of drawback or price cost for using this change data feed on top of Delta Lake tables, because under the hood for some operations, the file writer will not only write data files, so the files that are before your commit log sub Lake, we are going to record the changes for updates and the entries for deletes. And both files you can later retrieve in the commit log. So if you click Scott, it's kind of trade-off between the fast read and fast write, because on one side you penalize a little bit the writer with these extra files to manage and to write, but on another hand, your streaming readers can very quickly consume these changes without necessarily having some kind of reconstitution mechanism inside. So they can simply take the record from the CDC files and show and process and expose them to your processing logic. And there's also another kind of trade-off. Yeah, there is storage overhead for those files, but the good news is not for every kind of manipulations. It is only for deletes, merges, and updates. So when you are doing some inserts, you shouldn't be impacted that much. And for the next, yeah, there is, even though these change data feeds are not quite, I would say, public-facing files, they're also subject to the housekeeping operations like the vacuum, where change data files will be cleaned after your retention period. And but on another hand, they will not be impacted by Optimize, because Optimize explicitly filters out all files different than the additions, so different than this huddle highlighted add files in the commit log. So that was for the first feature. The next feature will be the truncate table. So it's kind of cheap way to clean up or the state of your table to prepare it for writing for rewrites. I call it soft removal because it doesn't need to touch the data. So when you run the truncate, you will not read the data files at all. Of course, it follows the Delta protocol semantic by creating a new commit for the time travel capability, and the files will disappear after the retention period, so the vacuum will reclaim the space after the retention period as for any other delayed operation or update operation. The bad news is the feature is only available on Databricks currently, so when you run truncate table on vanilla Delta Lake, you will not be able to get the results, but when you want to give it a try and see there is no data touched at all, you can check out the query profiler and analyze this IO part, and you should normally see all the zeros there. But there is hope, if I can say it that way. In the next slide, there is in Vanilla's Delta Lake, there is a way to simulate truncate table, because when you run that delete from your table or delete from your table and partition in the where condition, Delta Lake will simply analyze only the last snapshot. So I have some kind of animation right now where on the slide, yeah, it translates to delete command run that delegates the execution to delete command perform delete. That on its turn interacts with the snapshot to return all the active files that either correspond create a corresponding entry to the commit log with the delayed action and listing all these files that are deleted and read from this snapshot. That's great because you can simulate this truncate table. On another hand, when you go from some kind of more traditional world with relational databases, so that's a kind of gotcha I put on the slide for this simulating the truncate table. Yeah, there is a kind of animation that should popping right now. There is a semantic difference between truncate and delete in traditional world, because when you read the documentation of PostgreSQL, SQL Server, Oracle, you will see that there is a truncate is always associated to the metadata to freeing the space, whereas delete is always about touching and manipulating the file. So if you come from this word and you run delete from as a truncate, it may be a bit surprising to you. And that was the second feature. The third one is to decorate your commits with some kind of additional context. You can do it either per writer, or you can also configure Spark Session to use the same metadata for all of your writers. And it's pretty good because it gives you some additional information how each commit of the origins for each of the commits in the table. You could, for example, use it to annotate the data created from a reprocessing, from backfilling jobs. You can use it from a normal writer. You can add additional context like the version of the job, any other things you could retrieve from your deployment pipeline, or you could, for example, also put here some kind of confidence or accuracy scores, data quality measures, you name it. It's pretty flexible. It's a field that accepts everything. Like it's like the value field in Kafka, an arbitrary array of bytes. It's the same thing here. It's not constrained to any format or any schema. And in the next slide, you can see that how to retrieve this information from the describe history command and explicit select on the user metadata table. But again, there is kind of glitch for that, because remember, when its user metadata is per commit. So when you run some optimize operations, for example, it will obviously create a new commit, and this new commit will not take the previously, or will not do any kind of merge operation for the user metadata that is already present in the commit log. It does make sense, but it may be surprising. It was for me when I thought that maybe there is some kind of hope that optimize or housekeeping operations could do some merge for this user metadata part, but it's not the case. It does make sense, but in case it surprised you, now it shouldn't. The fourth pattern is about the constraints. So the constraints is like additional step Delta Lake offers to ensure good data quality. The first step is, of course, the schema enforcement. And the second ones are constraints. So there are three kinds of constraints you can define on your table. The not null that you can set when you create the table. You can, it's kind of requirement for the specific column to have some values. The simple checks that are value checks added by the add constraints command when you apply, for example, a value comparison or range verifications, like in the first line on your right. And there's also a possibility to write, it creates complex verifications with SQL expressions. And it's the example just in the middle, where depending on some value on another column, we are going to check whether the letter is different than X or different than two dots. So this is a kind of imaginary, but it's just here to show that you can really do some cross field references in these SQL expressions. And that's all for this slide. And the good thing to know is that the add constraint will fail if the rows that are already present in the table break the constraint you are trying to add. And it involves some changes in the writer part also. So whenever there is a new row to write by the Delta Lake writer, it will call an operator that will generate Java code for the validation expressions you just wrote. And later, it will perform the validation inside this write files function. If everything goes well, your data goes to the data files, but if not, you can The validation will stop at the first failure, so it can be a pretty cumbersome if you have many errors in your data and you discover them one by one on a big data set. In that case, it may be better to kind of pre-validate the data in a job that would that would generate a summary of potential data quality issues that break the constraints you just defined. And the second drawback is that the validation failure can leave orphan files that you are going to reclaim with vacuum with the vacuum operation. So that's yet another reason it's important to run this vacuum or to use the predictive optimization if you use Databricks. And regarding the five future, the clone, Delta Lake supports two types of clone. The shallow clone, where you only manipulate the commit logs, and the deep clone, when you literally separate the data of your table to your cloned location. And on the right, you can see two commands that you can use to create either the shallow clone or the deep clone. And the thing to know is that even though there is this shallow parameter that you can set to true or false, the deep clone will not work on vanilla Delta Lake, and you will get an exception that is not supported. So it's only supported as for today on Databricks. But again, there is some hope because you can simulate the deep clone with a native. Oh, sorry. Yeah, I was just going too fast. Yeah, we can discuss first the difference between these two. And the shallow clone, as I said, is based on the metadata. So we were on the good slide just in a minute. So if you can move forward, Scott. Yeah, the shallow clone is kind of interacting with this, again, with the snapshot of the table. So all the active data files at the current moment. And when Delta Lake calls this handle clone method, it retrieves all the active files from the snapshot and creates a new commit log in your clone destination. So you should see it just in a minute. Yeah, and you should have a new commit log entry on your cloned table location. But again, there is a drawback and kind of consequence for that metadata only linking. Yeah, that's for sure. The operation is fast because it only manipulates a kind of list of files and not the files themselves. But on the other hand, whenever you do some housekeeping operation, you vacuum or you optimize the storage, your original data files may disappear and your cloned table will not work. If it's your concern, you can use the deep clone, which is on the next slide, and simulate it in vanilla Delta Lake with the create table like command that will give you the schema of the table with all the metadata associated, like partitioning. And later, a simple read table from and append will copy the data files. So it will not copy data files as is, because you could also try to fine-tune this reading before by changing the size, the targeted size of Delta Lake files with the writing configurations, but it will copy the data without any modification anyway. And a kind of warning, you might be tempted by using CTAs for that, but bad news is create table as select will not preserve the metadata information about the table. It will just take the data as is, so without any partitioning, for example. And the final slide, the idempotent writer. So the idempotent writer is there to ensure you don't write the same data twice, assuming that your processing is idempotent itself. So whenever you run it twice or many times on top of the same data set, you always generate the same output. So with this feature that you can configure per writer with the transaction version ID or transaction application ID, or globally per Spark session with these two configurations, you ensure that whenever you replay the writer for the same version ID and the same application ID, the write will be skipped if the previous one was successful. And besides, if you use the Spark session configuration, you have this auto reset flag enabled that will reset the transaction version before, just to avoid you mistakenly retry the version with retry, for example, your streaming job without the same version with the same transaction version in this Spark session configuration, which would lead to skipped writes, so continuously skipped writes. And if you enable this flag, it's enabled by default, your writer will fail in that case. So if we go to the next slide. Yeah, that's how it behaves under the hood. Commit logs expose kind of in-memory map between the applications ID that wrote to this table at this point and the most recent transaction version. And delta lake command has been executed, interact with this table, and returns true or false depending on the written version and the most recent written version present in the commit log. And there is some kind of good practice or kind of quick win to use the microbatch number if you're running streaming for this transaction version, or you could, for example, use a timestamp or timestamp numerical value also for streaming jobs that you could retrieve, for example, from your input parameters. And there's also two things to know, if I'm not mistaken. First, the transaction at ID can be null, meaning that if you use only the transaction version and with your colleagues you're doing some test on development, for example, you might disturb each other and do not see the record you're supposed to see if you write to the same table. There probably also another one. Yeah, so the mapping is global. It's related to this cross-writers issue, and is the part. Yeah, it's your part, Scott, now. So thank you very much, and sorry for the issue, but yeah, we tested it before and everything works smoothly. But
It's part of what we do. It's it's all good. We made it through. We've learned the design patterns, and now we're going to talk more about those design patterns again. And we're going to kind of deep dive into something now just called like eventual extraction. And so also for everybody who's watching too, if there's questions, comments, anything else like that, we're going to open up around probably like 9:45 or 45 past the hour, depending on your time zone. And then so save any of the questions for the end, and then we can revisit any of them or kind of go into more details as well. Okay, so starting off with the design pattern of eventual execution. This is a pattern that came out during my time at Nike, and back when I was at Nike, we used to call this like the tin pattern. So if you think about like medallion, you think about like bronze and silver and gold, and this is all great. But tin was kind of this thing that we joked about because there was a lot of jobs that took data and made it available as kind of like, just like a landing zone. If you're familiar with like the landing zone design patterns or like kind of data domain patterns. And for a lot of cases, there is, certain issues with, a replaying, say 1 million, say I want to go and replay a job that had like 1 million hits to an API. Like you can easily create like a distributed denial of service attack on yourself by going back and trying to like replay the world. And so if you have an API and you want to be able to pull that data in, it's not like a very reliable source to go and stream off of, because in most cases, you're going to be chunking that by like, 100, 1,000 individual records at a time. And you're going to probably end up, that's going to take too long. And so the eventual extraction pattern can be used for any kind of like APIs or even just for Kafka, like in general. So if you have like a pretty aggressive delete policy. In a lot of cases, it might be 24 hours or 48 hours. By the time you go back in time to go and try and get data back, if you want to reprocess for any reason, a lot of times that data has already been either tombstone, partially deleted, and you're going to get failures if you go back, like fail on data loss is like a common option. And if you set that to true, you probably see that situation a lot. with like the Kafka stream for like their data stream v2, data source v2. But irregardless of all of that, the tin pattern allows you to essentially preserve the data as it was for as long as is safe or regulatorily acceptable for you to do as well. So we're going to walk into this pattern right now. So there we go. Okay. So what is eventual extraction, right? So it's kind of given like the overview for that. So it's basically pre-bronze and or like a safe space to, to kind of perpetually go back to. And so we essentially have like on like the screen, like we have like our tin layer, and that's great. And so like the first part of the job is essentially just taking the data source data as is, doing zero augmentation to it at all. But the other thing too is that like we care about the data being binary serializable. So if your data is coming off of an API and it's JSON data, it's not as safe to go back to because things could change like on that API for a specific version. So for me, I like to talk a little bit more about like Avro or Protobuf for things like this, where you have kind of constraints. Like I can guarantee backwards compatibility or can guarantee forwards compatibility with the data that I'm, kind of pulling out of like, long-term storage, for example. And so what I really want is to have like a very concrete, immutable per versioned, structured data that's going to be associated with the data I'm pulling out of, pulling essentially into the tin layer itself. So that if I decide that I want to go and extract this, 2 months down the line, 3 months down the line, et cetera, I can go back and ensure that it's not corrupt. And so we're talking a little bit about like backfilling and pre-validation before, when Bartosz was going through the different kind of design patterns earlier. And that's very important as we think about these types of design patterns, because the data no longer exists, which is like the first main point, right? The second point is that because it no longer exists, if it's corrupt, there's no way to get it back. And so that's a scary thing, especially if a job was botched, which we're data engineers, and data gets botched in production. It happens. And so this provides a way of kind of unbotching all of that, if that's like the right terminology for that as well. And so with that said, this is like a fairly simple example of this, right? So if I'm just using like the native Kafka data stream reader, and I want to go and load and create a data frame off of that, I'm going to always have key value topic partition offset timestamp type. This is great. This allows me to essentially mimic in a Delta Lake table what I'm getting directly from Kafka if I do absolutely nothing. And the big thing here is to do absolutely nothing. So we want to preserve everything as is, and we're going to go through kind of caveats as well after this, after kind of the completion of this pattern. But data quality matters upstream. And I'll just leave it at that for now. All right. So if we think about this reliable ingestion, right? I'm taking that initial Kafka data frame. Say I only care about the key value and the timestamp. I'm going to create a projection by doing a select against my data frame. And the neat thing about this is that because we have a data frame, and that data frame has a schema, which ends up being essentially like the struct type behind the scenes. Hold on. We can essentially use that to do something that I like to call steal the schema. So if we already know what our schema should be, then we can steal it from ourselves as long as we're writing like an initial table. And if you think about like the projection, it's fairly trivial, right? It's one dimensional. We have no nested types, anything else like that. Like it's a very simple table. But if you have like a kind of typical production table where things are complicated and they're complex, then this type of pattern allows you to create a non-trivial schema just by stealing it back from yourself, which is kind of cool. I'll show other examples of this as we go through this pattern as well. But aside from that, this is just a normal Delta table builder. And then when we call execute, it creates a table or it fails, depending on like, what permissions you have and things like that. And so really the big thing there is that we always want to steal from ourselves and be lazy wherever possible. So moving on, right? So if we have a data frame and it's essentially coming in from Kafka, we're doing a simple projection on that to create like our 3 rows, our key, our value, and our timestamp. It allows us to essentially create like an append-only log without like really having to worry too much about like, the initial partition where things came from or any of that stuff. So let's say like we're just creating a simple view of all transactions over time that we can essentially order by timestamp as well. And so that's what the end result of our Delta Lake table would be. So, and this is for the tin pattern, which is essentially the eventual execution pattern. So we're going to take our projection, we're going to write it, and we're also turning off overwrite schema, we're turning off merge schema. We want these things to fail, right? So if we're making an adaptive change to our table, and this is also like our source of truth to go back to, we want to be very cognizant of how we're changing things. Like for the most part, we're not doing anything fancy, we're not doing anything kind of custom, but just in general, if you can trust your upstream and you can, you want to be able to trust that anyways, but if the upstream is a trustworthy, like high quality data source, and now you're reading to essentially create like this, this eventual extraction landing zone table, or tin table, then having to deal with, conflicts and changes, it's always better to know before that ends up being something that's going to potentially corrupt, this kind of, this beautiful table that we're putting together. So with that, right, we've got a data stream reader, we're calling toTable on it. That's going to essentially write out to a managed Delta Lake table. The streaming query just allows us to monitor the behavior of that table. So if we're doing available now triggering, this might go for 2,000 transactions. This might go for 1 or 2, but we can monitor the progress as it's actually in motion as well. And so essentially the first half of the eventual extraction pattern is all about just doing absolutely nothing and trusting your upstream, data provider. So what does it end up looking like? Essentially your table, when you go back to go find it and you want to go take a look at it, right? We had created like a generate always as to apply a date so that we had something else to be able to query off of. We're using liquid clustering on timestamp, so it allows us to mitigate like partition boundaries, but sometimes you still want to go back to specific dates and points in time. And so this allows you to have the best of both worlds while clustering on timestamp, which is pretty tight. But the other thing too is that like the keys and values don't really matter, right? Those have to be extracted first. And so your key can be complex or simple because it's just bytes. So you can literally pack that and put any data you want in it. It could be AVR, it could be protobuf. The same thing with your value as well. So it allows you to essentially have like, 2 specific kind of points of interest per record, which is neat. So there's other patterns we could go into, but we don't have time for that. So I'll just kind of cruise along through this. So big thing, the data looks absolutely no different than how it came off of Kafka, minus, some of the metadata, like any of like the actual like offset information, things like that. So we're just preserving like the core information. So the second part, right, if we had the eventual extraction, we want to go now extract our data at a later point in time. This could be a minute down the road. This could be, again, 2 weeks down the road. It could be a month down the road. But the thing is, you're going to use this however you want to, right? Like if you need to go and reprocess, you want to go reload data, that's perfect. If you want to go and, essentially do a backfill because like other things kind of broke with an upstream system, you can still go and do all of that. And it still gives you that safe space to start from. And so like here, like I was kind of calling this, like I was going back and forth with like how to actually like name this, right? But if you think about like, ELT or any of the other like design patterns for like extracting, loading and transforming or transforming and then loading like our data, this kind of can, play in that, same kind of pond. The big difference is like, if you want to go all the way back to your binary data, then you have to essentially do your extract first from like your binary into something that is like a data frame, so a catalyst row. Then from there, any kind of transformations to go and create that bronze level table that is like your reliable source of truth for your data. So this pattern can simplify reprocessing of any kind, with the caveat being that it expects edge level data quality rule enforcement. So what does that really look like? So in this case, I'm going to show like a protobuf example. So we have our raw data, which is coming in from Kafka. We've got our value, which is just like a byte buffer. It's a payload that could be something that's arbitrary. And we're going to deserialize that using like a descriptor, which is essentially saying like, here's the schema of these binary bytes. We're now going to convert that to go and create like a catalyst row. And then we're going to go and, I'm going to alias that row as an order record. So I'm now doing essentially select date, timestamp, order, and I'm just converting like my value bytes to that actual order itself. And so this allows you to essentially do that first level of extraction. And so from the first level of extraction, we'll see that like we essentially go from just bytes to order, which actually has structure. And so this is that initial extraction. And so this allows you to essentially kind of preserve stuff like on ice, like for later, when you want to go and extract it at a point in time where you want to actually use this data. This gives you a very solid way of going back and actually doing that as well. So this kind of like this preservation pattern came out of time at Twilio back in like 2017. So a long time ago, but this worked really, really well for us being able to go back and like run a lot of different kind of custom jobs and things like that, where we had a lot of data, but we didn't necessarily want to store all of that data in a single large table. So we wanted to be more kind of cognizant of what data we pulled out, you know, as we were actually, you know, working with this pattern as well. And so if you think about being able to pull out like an order and then being able to query that order and then go in and create like a, you know, fit for purpose table from that extraction, then it gives you essentially like a two-step problem to solve that gives you then a very reliable way of creating source of truth data or foundational data. So we'll take a look at that too. So if we take a look on the left, essentially we have an order. So say, for example, you wanted to go and like, you know, flatten your nested data. So like where we have like order created, now I want to create an alias on that just called order created. Same thing with like, you know, if I have an order object that then has a customer with a UUID, I want to pull that all the way back up so it makes it easier to query. We can do that. You can also use dot notation. Really depends on like who's querying and, you know, what they actually want to work with as well. So I usually like to just preserve the nesting, but it's really up to the engineer and figuring out what they want to do moving forward, right? So we transform our nested data, we're creating flattened rows. And then I'm also like, in this case, I want to create like an order total, like based off of each sale. And so I'm just essentially lifting that back up into its own row. So I'm just concatenating essentially like units and nanos, which is part of like the default protobuf for Google Money. The nit for all of this is that like, if you want to have like a shared, like formal, like foundational table, then people can't always go back to the source of truth, which is fine. In the past, I've talked about like internal and external data domains. So like within like an internal data domain with like, you know, people within your org that you can communicate with like on a daily basis. If things change, it's a little bit easier to communicate kind of changes within that internal domain. Once things are published into like, you know, gold tier, et cetera, like this is like our fit for purpose data. Any of those tables, then people wouldn't know that, you know, you have like these bytes lying around, and they wouldn't really know about the eventual extraction pattern either. So it's more kind of an internal concern for teams that are on the hook for data quality and things like that as well. It really gives you like a powerful way of moving back in time. Okay, so we got that. Same thing again. So if we have a transformed schema and we want to be able to ensure that that's going to always be like our table, like, you know, our table schema, we steal the schema again. The other nice thing too here is that as long as we continue to say overwrite schema false, merge schema false, then we're very, like in this case, like we're very specific about the way that the actual schema of the table changes. So if we botch like our transformation and we add new things, we're going to essentially hit like that kind of hard constraint. So different type of constraint, but it's ensuring that our schema of our table doesn't evolve outside of our notice, right? And so we'd rather have a job fail than potentially have like a breaking change go downstream. So a lot of these like design patterns are also just about the data quality itself. The other interesting thing too is that like I've highlighted essentially like in the comment, like if you don't have data, like any kind of data lineage, and you want to like track, you know, kind of simple information about like upstreams and like what's actually being created, that's also things that you can add to like the table metadata to allow people to kind of query that and figure out more about like the lineage. Or you can use tools like Unity Catalog and things that support lineage between tables as well. But this is a very kind of simple trick for doing that, which gives you at least a place to go to figure out like what the upstreams are, et cetera. And it's a nice use of metadata. So we'll now take a look at like the entire eventual extraction pattern in essentially like in practice, right? So I have a table. Yay. That was our source table, which is essentially just like our key or value or like our timestamp and the date, liquid clustered by timestamp. That's cool. We want to read that stream. So we're taking like our, you know, so there's an option here called with event time order. And the interesting thing that is like for every transaction, our event time doesn't care about the file time, like when something was written to like the operating system, but it cares about the timestamp that's actually done on the transactions itself. And so if you think about like add files, there's like metadata about the time that things were actually committed. So event time order will allow you to actually preserve like the true insertion order versus dealing with any kind of issues in the file system for when things were actually written. And so like if you're reading from a stream and things might come in out of order, with event time order, it gives you a different way of actually ordering that data. And so I found like with streaming, it actually works a lot better to use with event time order for that if you want to preserve essentially like the history in correct sequential time. So in this case, we're going to create a read stream off of a managed table. We're doing our select. We're creating like our protobuf like extractor. And then off of that first extraction, we're doing a second order extraction. So you'll see there's two select statements. In the second select statement, all we're doing is flattening the table again, and we're creating our column. So it's all the pieces that we saw like, essentially in phase in sequence. Then at the very end of that, we're doing like append only to our Delta Lake table. We're doing available now triggering, which is one of my favorite ways of triggering streaming jobs. And then that's also going out to the new managed table, which is the coffee V1 orders base. So base, bruns, whatever you want to call it. I think about this as a foundational table because now things have been extracted and we can use it for a specific, specific reason. Again, caveat, this requires high quality data from the source. So if there's problems that are coming from like, any kind of issues with upstream data providers, this pattern wouldn't work as well unless you have a different kind of layer of like protection before the data actually makes it into your tin layer. And with that, we're going to break into Q&A. And so Bartosz, if you want to come back into the session, then we can answer any questions people have, or we can just talk about design patterns more, just in like a more kind of conversational way. So if there's any questions, please let us know. Or I'll just chat with Bartosz. So let's see. Okay. Okay, cool. I'm going to go, hold on. Let me go take a look at the chat. Okay. Let's see. All right. So Bartosz, do you want to answer this first one? The question is, if we enable the Delta change feed per session, does it mean the data is only accessible in that same session?
No. The Spark session configuration is for all operations made within the session. So if you create a change data feed table, so if you create a table and you enable the change data feed at the Spark session level, the change data feed will be enabled on that table automatically without having to set the table property. It's pretty convenient if you have to create multiple tables within the same session, so you don't need to worry about these extra configurations each time. But there is no link with the change data feed availability for the consumers.
Awesome. I'm like that. That's a great answer. Let's see what else we got. So awesome. We've got a lot of hellos from all over the world, which is wonderful. Let's see. So we got that one over there. So there's another question that came up essentially about like the tin layer. So it's like, what's the advantage of the data deduplication between Kafka and the Delta table itself? And so it's not really like, I wouldn't call it like deduplication or the duplication. Sorry, I was reading that wrong. I've got dyslexia. So the data duplication, the reason for this is essentially just like if you've ever been paged and you have maybe an hour to get something fixed because Kafka is expiring the data that needs to get fixed, this is a way of mitigating that problem. And so like, if you don't want to get paged and fix a problem within, that window where data is expiring, this is a great way of going back in time. And then Bartosz, if you want to talk about like hybrid source or anything else like that, like there's other reasons for having like a copy of the data in a way that's easy to get back to.
Yes, one of the reasons is the hybrid source, like you mentioned, Scott, is when you want to create a streaming applications, for example, with Flink or Spark Sector Streaming, and you don't have all the historical data available on your Kafka, so that you can first process or backfill the historical data, create some initial state, and later move on to the real-time data on Kafka. And also to complete, there is also more convenience to you as an engineer to work on Delta Lake tables for all cumbersome tasks like database. You can particularly target a tenant. So for example, one customer and they process his data, versus when you don't do this duplication, you will have to kind of stream all the changes from your input topic and filter out at the data processing logic, which is much more harder than just adding the where condition in SQL.
Yep. I think it's also interesting too, right? Because if you've ever restored from Kafka with like a non-trivial number of partitions, there's a lot of offsets for your starting offset. So there's a lot of offsets for your ending offsets to manage. If you want to go back to a very specific batch of data, it's much easier to say starting version, ending version, like for the transaction log in Delta, to find like a very specific chunk of time, like transaction 100 to 120 is a lot easier to be able to understand, because you can go back to like the Delta history to find out all the information as well. And so like in the theme of like being lazy wherever possible, like complexity is nice, but laziness is much better. And so that's like a really nice pattern. Starting version, ending version. I see there's a comment. It's like with Flinkster, we don't use that here. Perfect. That's okay. At the end of the day, like whatever engine you use for Delta is perfect. And there's pros and cons for everything for that as well. So, okay. There was another question. It says, if the Spark stream is running in microbatch mode, when will the next batch be created? The real challenge is that our pipeline has multiple layers, raw, bronze, silver, curated, etc. Notice a delay in data arriving in the gold layer. What could be the reason for that? Bartosz, do you want to take a shot at this one? There's many reasons why things could be delayed, but
I have only the simple answer that the next microbatch will be created after the previous completes and if there is new data to process. But I didn't get the full picture here because I focused on the first part of the sentence. So maybe Scott, if you complete.
Yeah, no. So it's like, so I think, so it depends, right, on your triggering, right? So if you're triggering and you're doing process time, that's going to essentially run, your next batch will be like, 1 minute after your last batch is completed, because that's the next time it's going to basically tick. So it's going to essentially, like if you say I want to process every minute, but it's taking you like 30 minutes to complete one essentially loop, you think about one microbatch completing and committing, and then making it to that next stage of execution, then even if you say every minute, this is going to process every 31 minutes. So it's going to be like, okay, cool. This is running. You're not going to have like multiple like loops running at the same time, unlike a lot of like the scheduled like thread executors or anything else like that in Java. And so depending on like what you're using, so I saw there's also a question about available now processing or triggering. So like if you say trigger available now, and the last time you ran, your workflow or your job, and say there was like 50 transactions that occurred between the last time you ran and like the time that the job kicks off, available now will just go through honoring all of your throttles. So if you have like max files per batch for microbatch, et cetera, like anything that's like essentially creating like a very finite chunk of data to work on, all that will be essentially honored on your behalf, which is nice. Versus like available, like if you do like a trigger once, it's going to potentially load up everything and you're going to run out of memory. And processing time is going to take could take a long time to basically catch back up, because it's going to synthetically add time between each time you tick. So if you're saying processing every 5 minutes, but you have 50 batches to essentially catch back up on, then it's going to take you at least like those 50 minutes to go run everything, when it could just be 1 minute. So doesn't really answer the root question, which is like why things could be delayed. And usually things are delayed, depending on the number of handoffs, right? So if say there's a team that's writing to raw or like to the tin layer, and then another team is extracting that from tin to bronze, and say they're using like a, like some sort of like cron job, anything else like that, scheduled workflows, then it could take like a long time between, the time that data is essentially ingested into raw, then going to bronze, and going to silver, and going to gold, or any other kind of curated layers, versus essentially having that all be like in like one, workflow as well. So it's a streaming job in continuous mode. it's using autoloader for reading from S3. Bartosz, do you want to talk a little bit about like autoloader? Do you want to talk about like Databricks workflows at all?
I don't get this question, to be honest.
So I think for this one, so like if you're using like I think it was like the format cloud files was like the autoloader. So if you're reading from like S3, okay, so they're doing like SNS notifications for this. So this will still run. So like this is like Learn Hadoop who's asking like this question off of YouTube. And so if you have like a lot of like, if you have like SNS notifications or anything else like that, that's then triggering like a batch of execution. If there's any other delay, that would be like the delay in running like that pipeline itself. And then I'd have to see the job as well. So like, I'm like, if you want to learn, I'm like, whoever is behind Learn Hadoop, I'm like, if you want to reach out like on LinkedIn or reach out on like the Delta Slack channel, I could find out more about like what could potentially be causing this problem as well. So I don't, not enough information for this one right now. Let's see. Any other questions? So yeah, 60 minutes to reach the raw layer. Yeah, that seems high. We're looking in the comments right now. So this is another one from Learn Hadoop. So if your initial ingestion is taking like 60 minutes to reach the raw layer, it would depend on like what does the data actually look like, right? If it's S3, it could be essentially like, it could be kind of anything, things like that as well. It's like, is it raw Parquet data? Is this JSON data, CSV, anything else like that? Like all those, formats change the way that something can actually be read in that initial batch as well. Bartosz, if you want to answer anything there as well. So I'm just kind of spitballing off of these, off of the questions.
As we ask, it can be anything. It can be the infrastructure, it can be the code, it can be maybe the different regions in your cloud provider that add some latency. All of those things, and yeah, it's kind of difficult to answer this kind of high-level questions without having low-level details.
Yeah. I think with the JSON data, it just depends on like the complexity of like that data as well. It also depends on the total number of like files itself. So like if you're writing a lot of small files and those small files have to be read in using autoloader, then it really depends on whether or not that, that batch is taking longer. So I think that's also something that, I don't know. There's many different reasons for it, but it might just be that you need to add more compute nodes to be able to like distribute the job more. Because sometimes reading from S3 takes a lot of threads. So, so yeah, we'll move on. We have one last question as well that just came through it. So is data lineage only in comments or can it connect to open lineage lib? And so for Alexander, like for this question, I threw it into the comment essentially like in a case where you don't have like if you're not using like say like paid Databricks and you don't have like Unity Catalog's lineage feature, or if you're not using something like a Calibra or anything else that also has like data lineage or any kind of like tracking, and you are using like open lineage, then essentially like anytime like you create or you change a table or you change that comment in the table, it's like just basically like a metadata only change to that table. You'd have to be able to essentially just track those changes. So like I just wrote like a simple comment that was using like a colon separator. You could also pack like a JSON blob into the comment as well. If you wanted to, you could add this as like a table property to the table as well. So you could manage like multiple sources in a different format. It's essentially just a way of saying like, every time like a table is created that has like an upstream or it has multiple upstreams, or it's, doing joins on those multiple tables as well. Like being able to know what could potentially be causing problems at a certain point in time within like, the medallion architecture with, whatever, data architecture you're using for, getting data into your system and then out to some sort of, analytical query, et cetera. It's one way of doing that. But if you don't usually, like, if you don't track that as part of, the way of working, things get a little bit more problematic to go back and like retroactively add all this information. So it's more of like, a way of working. So it's like, oh, if we're going to create a new table, then we need to add a comment that, gives us some sort of lineage information in there as well. Okay. Let's see. So there's also another one. I don't know. we could go for one more question, I guess, as well. We're a little just over time, but there's so for batch processing, does eventual execution still work? And the answer is yes. So whether you're reading stuff in batch, it showed some examples, and we'll share the slides afterwards as like we'll basically share like a slide share link for all of this as well. So being able to have that pattern work for batch is like kind of the beauty of it. So you can extract this for anything you want. Streaming is nice because a lot of like batch problems, you want to be able to work on things in batch and then scale up to stream as well. Let's see. I think that there's a couple other questions that are kind of continuing to go on as well about like the Spark UI and stuff. But I think for now, given that we're over time, I think we're going to close out for the day. So we'll share the slides with everybody else afterwards as well. And thank you, Bartosz, for joining and for getting through this as well and getting through like our second webinar together, which has been awesome.
Yeah, it was a pleasure. And for the next time, I already have a Mac, I promise.
Forward progress. That's awesome. But yeah, no, that's yeah, this stuff always happens. So it's all good to know. The permissions models are always hard. So we got this. So thank you everybody for joining, and please come for any of our next sessions.